Good afternoon, everyone. In the beginning of the class, let us see new announcements. Okay. Okay, the first new announcement is May 18th, 2022 class videos uploaded. Hello everyone, I have uploaded the class videos on May 18th, 2022 to YouTube. Their URLs are this, and this. Okay. Best regards, Wei Zhen. Okay, the second new announcement is the computer program of page 37 of chapter 4 has been uploaded. Hello everyone, I have uploaded the computer program of page 37 of chapter 4 to the eCourse 2 website. The location and the file name are eCourse 2 website, multiple input, multiple output techniques for wireless communications, course content, computer program, chapter 4, page 37.m. Okay, best regards, Wei Zhen. Okay, the next new announcement is please complete the teaching questionnaire for EMI course. Okay, what is EMI course? The EMI course means that we teach the course totally in English. Okay, hello everyone. As the semester draws to a close, I encourage you to complete the EMI course teaching questionnaire by June 5th, 2022. The results of the questionnaires will be used as a reference for teacher award applications, student counseling, and English proficiency improvement activities in the next semester. Okay, here is the teaching feedback questionnaire for EMI courses student version. Okay, and this is the URL, okay, in English, and here is the QR code. And here is the 全英语授课教学回馈调查问卷学生版 and this is the URL, okay, in 中文 and this is the QR code. Okay, best regards, Wei Zhen. Okay, the next new announcement is the slides of chapter 4 has been updated, version 2022-0523. Hello everyone, I have uploaded the latest version of the slides of chapter 4 to the eCourse 2 website. The location and the file name are eCourse 2 website, multiple input, multiple output techniques for wireless communications, course content, slides, chapter 4, slides 2022-0523.pptx. Best regards, Wei Zhen. Okay, the next new announcement is the handout of chapter 4 has been updated, version 2022-0523. Hello everyone, I have uploaded the latest version of the handout of chapter 4 to the eCourse 2 website. The location and the file name are eCourse 2 website, multiple input, multiple output, Techniques for Wireless Communications, Course Content, Handouts, Chapter 4, Handout 2022-0523.pdf. Best regards, Wei Zhen. Okay, next let us look at the progress of the last class. Okay, in the last class we have taught to chapter 4 slides, page 40, table 4.1, the row indoor obstructed. Okay, finished. Okay, so please open the slides of chapter 4. Okay, and please turn to page 40. Okay, we are talking about table 4.1. Typical path loss exponents for various propagation environments. So the last row is the IEEE 802.11n. Okay, what is this? Let us see the handout. Okay, search for the IEEE 802. Okay. Okay, IEEE 802.11n. Okay. So page 40, problem 1. What is IEEE 802.11n? Okay. Solution: IEEE 802.11n-2009 or 802.11n is a wireless networking standard that uses multiple antennas to increase data rates. Okay, so in the environment of IEEE 802, okay, .11n, the exponent is equal to 2 before dB, where dB is the breakpoint distance, and the exponent is equal to 3.5 after the breakpoint distance. Okay, this comes from reference 26. Okay, let us see a reference 26. Okay, the author is Ersek. Okay, it is the title of the document is IEEE P802.11 wireless LANs TGN channel models. Okay, and this is the number of the document, which is published in May 2004. Excuse me. Okay, the last entry specifies the exponents used in the official propagation models defined as part of the IEEE 802.11n standard. Okay, here, which is primarily concerned with indoor propagation. We see that the exponents for the 802.11n models are similar to the theoretical two-ray values. Okay, in the theoretical two-ray values, before dB the exponent is equal to 2, and after dB the exponent is equal to 4. So next let us go to section 4.3, impulse response of a multi-path channel. This section lays the mathematical foundation for characterizing the details of multi-path behavior. To do this, it is convenient to view a multi-path communications channel as a filter, which allows us to use some of the concepts in filter theory to help describe multi-pass channels. One of the fundamental properties of a filter is its impulse-response function. Therefore, we consider the impulse-response function of a multi-pass channel in this section. We start by considering a general transmitted signal, S of t, which we can write as follows. Okay. S of t is equal to the real part of u of t times exponential j2 pi fct. Okay, the equation number is in the wrong place. Let me correct it. Okay. It is strange. I cannot put the equation number in the correct location. Okay, so let us skip this. Excuse me. Okay, where u of t is the low pass equivalent, LPE, of the signal, and Fc denotes the carrier frequency. Excuse me. Okay, I think you have already learned what is the low pass equivalent, LPE, in the course Principles of Communications, or the course Digital Communications. Okay, if you forget what is the low pass equivalent, please review the textbook of the Principle of Communications or Digital Communications. Okay, if you did not take these two courses, okay, then you can go to the internet and search for low pass equivalent to understand the related topic. In a multi-pass environment, the received signal arrives over multiple paths with different gains, alpha I of t and delays tau I of t. Okay, where alpha I of t is the gain of the ith pass at time t, and tau I of t is the delay of the ith pass at time t. Okay, the resulting received signal is therefore given by, okay, x of t is equal to summation I, okay, because there are multi-paths, so we need to sum them up, okay, for each I. Okay, alpha I of t, because alpha I of t is the gain, okay, so it must it must be multiplied in front of the signal s, okay, and s of t minus tau I of t, okay, because tau I of t is the delay, okay, so we let t minus tau I of t, okay, then s of t will shift it to the right by tau I of t. Okay, so it is the delay. Okay, and this is equal to summation I, alpha I of t, which are the same, and s of t minus tau I of t. Okay, you can obtain this by replace this t by t minus tau I of t, and replace this t by t minus tau I of t, and also replace this t by t minus tau I of t. Okay, so s of t minus tau I of t is equal to the real part of u of t minus tau I of t times exponential j2 pi fc times t minus tau I of t. Okay, and we can move the real part operator out of the summation like this. Okay, it will not change the result of the equation. Okay, then sigma I is here, alpha it is here, and u of t minus tau I of t is here, and exponential j2 pi fct is here. Okay, because this term does not depend on index I, so we can move this term out of the summation. Okay, and exponential minus j2 pi fc tau I of t is here. Okay, where the term in brackets is the low pass equivalent of the received signal. Okay, let us see, this is the term in the brackets. Okay, is the low pass equivalent of the received signal. We denote the low pass equivalent of the received signal by R of t, which has the following form. Okay, R of t is defined as summation I alpha I of t times u of t minus tau I of t times exponential minus j2 pi fc tau I of t, okay, which is just the term in the brackets, okay, here. Okay, based on these definitions, we can formulate the low-pass picture of a multi-pass channel as shown in figure 4.5. Okay, let us see figure 4.5. Okay, in this figure, figure 4.5 shows a low-pass channel model. The U of t is the input signal of the multi-pass channel, and this block represents the multi-pass channel, where C of t tau is the impulse response of the multi-pass channel. Okay, you may have a question: why are there two variables t and tau in the impulse response function? Okay, we will explain what are t and tau later. And R of t is the output of the multi-pass channel. Excuse me. So this figure depicts the low-pass equivalent input to the channel U of t and the low-pass equivalent output of the channel, that is, the low-pass equivalent received signal R of t. Okay, U of t and R of t. Okay, the channel itself is modeled as a filter with a linear time variant LTV impulse response function C of tau t tau. Okay, please recall that when you took the course, excuse me again, signals and systems, or the course principles of communications, the impulse response you encounter is linear time invariant. Okay, that is LTI. So now we go further. Okay, we have the linear time variant LTV impulse response function C of t tau. Thus, the received signal is equal to the convolution of the transmitted signal with the impulse response of the channel. Okay, at a given time t, R of t and U of t are therefore related as follows. R of t is equal to C of t tau star u of t, where star denotes convolution. Okay, and this equation is equal to the integral from minus infinity to infinity c of t tau times u of t minus tau d tau. Okay, please note that the variable of the integral is tau, okay, not t. Okay, so you can see that here is tau and here is t minus tau. Okay, so this is the form of convolution. Excuse me. We will find it useful later in the chapter to express the received low-pass equivalent signal R of t in terms of the Fourier transforms of small c of t tau and small u of t, which we denote by capital C of tf and capital U of f respectively. It is straightforward to show that, okay, R of t is equal to the integral from negative infinity to infinity capital C of tf times capital U of f times exponential j2 pi ft df. Okay, where capital C of tf is equal to the integral from negative infinity to infinity small c of t tau times exponential minus j2 pi f tau d tau. Okay, so the capital C of tf is the Fourier transform of the small c of t tau. Okay, and please note that the variable of the integral is tau, okay, not t. Okay, it is very important. And capital U of f is equal to the integral from minus negative infinity to infinity small u of t times exponential minus j2 pi f tau d tau. Okay, so capital U of f is the Fourier transform of small u of t, and please note that the variable of the integral is tau, okay, not t. Oh, so it should be tau. Okay, sorry. Okay, so please fix it. Okay, it should be u of tau, and I will upload the correct version of the slides later. Okay, let us see the next page. Okay, in order for equation 4.11, okay, let us see equation 4.11. Okay, this equation, okay, R of t is equal to the integral from negative infinity to infinity C of t tau times U of t minus tau d tau. Okay, this is equation 4.11. Okay, to give the same expression for R of t as in equation 4.10. Okay, let us see equation 4.10. Okay, so in equation 4.10, R of t is defined as summation I alpha I of t times U of t minus tau I of t times exponential minus j2 pi fc tau I of t. Okay, so the impulse response function must have the following form. Okay, let us see this equation. C of t tau is equal to summation I alpha I of t exponential minus j 2 pi fc tau I of t times delta of. Okay, it is 25 minutes. Let us take a break.